then this is scheduled to be complete in 2012, and we are starting construction next year. And then, so this building, first thing has a structure. We have a structure, concrete and steel structure, and then we have concrete core, and that is covered by a diagonal structure, which is weaving the whole tower together as a shape structure. Another thing about this project is that it has a shading exterior skin, which is a stainless steel mesh, 50% transparency, and there's 5,000 of them. And we try to keep the consistency and complexity, but still we need to rationalize them to get it. And I start talking about the structure, how it's modeled, and this animation is a screen capture of the software we are using. I happen to have my personal 3D modeling software I've been developing for 3 years personally, and I'm using that. And usually, to model diagonally, you select the one surface first, and you just map the diagonal grid. But the problem is we have very irregular shape and high specific boundary condition. And to work with boundary condition, if you just trim the one big surface, you just end up a small triangle that are matching edges, which doesn't work all with structure. And another way to do that in traditional area, you might be able to simplify the original geometry into simple entities like bottom diagram, like the 4 simple surfaces, and you can build a diagram between them. But you have to stitch them, and the stitching cannot be smooth always. So I to different approach, I built a different system applying the autonomous behavior to geometry. So those points are free to move on sectional curve, and then they are bounded by the diagonal line which has tension. So basically, this is just a simple tensile mesh simulation, but working perfectly with irregular boundary condition, and then when they could get the equilibrium, that is the smoothest geometry we can. But there's another problem about making them smooth, because we want to get it cheap, and then usually the maximum complexity and the consistent smoothness create unique geometry, which is all custom-made unique geometry, which is really expensive. So we want to repeat as many of same family as possible, and then in this geometry, the gray areas are unique, then the colored areas within specific family, they are exactly the same shape. And so there's a history of how we rationalize them to maximize, plus keeping the consistent geometry and the balance of structure and the form. And then so we are maximum that kind of rationality until 2007. We suddenly changed the criteria, which frequently happen in our office. And one day structure engineer came, and if we increase the vertical structure member, that can be cheap, because now you can see that as not diagonal, but you can see as column, and you can see another diagonal line as a bracing. Then they apply different type of formula for column and the bracing. That is amazingly thinner than diagonal. So now we change the diagonal line to vertical, and then sacrificing some part of repetition. And the current one is the right one, which is we remove some unnecessary bracing, and then now we got that became a hybrid structure of diagonal and then column bracing, and then in gradual way. So that is an efficient way. And then same thing happened to grazing geometry too. And that we used to have a triangulated panel. We don't have any curvature grazing, so we have to make everything flat. And then, but the problem was there's a huge requirement from program. This is office building, so we're gonna get tenants, and the tenant, we don't know what kind of office space tenants want. So all the million line, the grazing have to perfectly match with the interior space planning grid for them to get wall afterwards. But the problem is the diagonal was the diagonal line doesn't always match with those lines. So then that ends up really huge joint and small triangles, and very expensive. So we changed the scheme to radial scheme. So radial scheme could make a radial grid at the corner, and then that which is perpendicular to the specific location which matches the orientation building. And then checking the highest sum, which is always summer solstice sum. And then it rotates itself to find the maximum shading area. Then actually that can be calculated by just a vector mass or using cross product. So in that sense, like south faster panel find the sun around noon, and then that is optimized for it. Then like east faster find the morning sun, and that is optimized for that. So this diagram shows there's a number and there is a time. They have all different time which all panels are optimized for. And this is showing the next step of rationalization of the skin. Because skin is following the original smooth shape, we are trying to keep smooth, nice, consistent geometry. But that ended up really 5,000 different size of panels. They are all rectangular but still dimensionally different. So this script just round up size, so shrinking the size to specific size, and then maximizing the family. So then, of course, we made a lot of study like changing the unit number, like 10 centimeter each or 20 centimeter each, and what is the visual impact of the having more gap. And so then we can compare how much of member is repeated and how much cheaper. And at the same time, this is generating analyzing the order angle for the joint. And then structure engineer work with the structure joint. Then they have to know the polar coordinate converted angles to design the joint. So then this is just technical side of that. How we organize the software. We use many different softwares, and then actually our major platform is MicroStation, and I'm building Java software. And the Java software, the MicroStation has a parametric modeling environment genetic components. So I'm writing a genetic component script inside my software. So I'm making a software to write script. And I'm doing the same thing for digital project Katia. So I'm writing. So each of the geometry is converted to script and having some parameter, keeping some parametricity which can be edited inside those parametric environment. And so in a sense, I'm building a meta script